We're going to cover redox today. This is a really important topic in A-level chemistry because it underpins a lot of how different things react and so on. It's the basis for a large amount of particularly Module 5 chemistry. Okay? And it's not actually that hard. So, we're going to be looking at the definitions of oxidation and reduction. We're going to be calculating an oxidation state. We're going to be doing the rest of this, where we're going to end up, hardest part of it, balancing ionic half equations and then combining them to form a redox equation. So, oxidation is obviously the gain of oxygen. And we all know this, we all done this at GCSE. When carbon burns, it adds oxygen to form carbon dioxide. That's oxidation. Another definition of oxidation is it's the removal of hydrogen. Okay, an example of this would be when ethanol gets oxidized to ethanoic acid. Okay, it actually loses a hydrogen in the process. And we're now defining oxidation as the loss of hydrogen. So we've got two definitions so far, the addition of oxygen and the loss of hydrogen. Reduction is the exact opposite. Okay? If you oxidize something, you add oxygen. If you reduce it, you remove oxygen. That's nice and straightforward. And it's also the gain of hydrogen. As in ethene plus hydrogen goes to ethane, we're now defining that as reduction. Okay. You may or may not remember from GCSE, there is another definition. And this is in terms of electrons. Oxidation is the loss of electrons. Reduction is the gain. Okay? Do we remember this? And the way to remember it is oil rig. Oxidation is loss. Reduction is gain. Are we happy with that? Yep. And you got a nice little picture of an oil rig there. Okay. We're now going to move on to the A-level material. Oxidation states. Okay, to begin with, these are a bit tricky, but then you get your head around them, and they're really, really easy. So, sodium. In sodium, it's got an oxidation state of 0. Any element in its standard state, oxidation state 0. When sodium becomes +1, okay, Na+, we say it's got an oxidation state of +1. When chlorine gains an electron, it's got an oxidation state of -1. Don't worry too much about this way of working it out. It'll become very clear in a moment. But 3 oxidation states to begin with. Element, 0. 1 plus iron, +1 oxidation state. -1 iron, -1 oxidation state. Could you pause please for a second? The way that you work out oxidation state is that the sum of the charges equals the oxidation state. So if it's got no charge, the oxidation state is 0. Single iron, becomes more complicated ones in a minute, +1 charge, +1 oxidation state. -1 charge, -1 oxidation state. Therefore, the oxidation states of the following are very, very straightforward. 0, +3, +2, -2, 0, +3. So far, so easy. And I've got it right. Good. However, okay, hydrogen in H2, 0. Carbon in carbon dioxide is +4. It turns out there's some elements that you're expected to know what the oxidation state is. If we scroll back to here, we can see that the oxygen's got 2- oxidation state. You happy with that? And that is its standard oxidation state. So if it's 2-, then does it make sense that carbon's +4? If oxygen's 2- and you've got 2 of them, that's effectively -4, yes? And I'm telling you, and it's probably worth writing down, the sum of the oxidation states equals the charge. Okay? The sum of the oxidation states equals the charge. So, if you've got no charge, which you haven't on CO2, okay, no charge, it means the oxidation states add up to 0. If the oxygen is -2, and it is, and you've got 2 lots of -2, well that's -4. What added to -4 equals 0? And the answer is +4. So, carbon's +4, and the oxygen is -2. Are we all good so far? Yep? So, there's my explanation. It's neutral. Some of the oxidation states must be 0. One's got to be positive, the other's got to be negative. Oxygen's -2, therefore carbon's +4. Right. This is where it starts to get a little bit tricky. By definition, we say the more electronegative species will have the negative value. In almost every example you're likely to be asked, oxygen's going to be negative. Okay? But there are some elements where it could be both positive or negative, depending on what it's combined with. Chlorine's a good example. Chlorine's usually -1. But when chlorine combines with oxygen, such as a chlorate, the chlorine becomes positive. Okay, and you can get the +1, +3, +5, and even +7 oxidation states. The only time oxygen has a positive oxidation state is when it is combined with fluorine, which is more electronegative than oxygen. Okay? So, very simply, it's based on the position in the periodic table. There are some that you're expected to know. So, in NO3-, the sum of the oxidation states is -1. Okay? Because that's the charge on it. We said that oxygen's -2. Anyone want to yell out what the answer is then? What's the oxidation state of nitrogen there? If oxygen's -2, the sum of the charges, the sum of the oxidation state's -1, what's N there? +5. Okay? Absolutely standard AS Module 2 question. What's the oxidation state of nitrogen in NO3-? And the answer's +5. If we think about it, +5 minus 6 equals -1. So here, what's the oxidation state of the sulfur? Everyone just take a minute, try and work it out.
6.
And then don't yell it out, but okay. Is there anybody in the room that is not happy that sulfur in this case is +6? Be honest. 4 lots of -2 is -8. -8 minus -2, okay, is -6. Therefore, sulfur has got to balance out -6, which means it's +6. Here, okay, if hydrogen in this case is +1, what's the oxidation state of the nitrogen? Did I hear a +3? +3 is wrong. -3. Okay? -3 plus 4 equals +1. You happy with that? Okay. More complicated ones. What's the oxidation state of manganese in the manganate ion? Well, the oxidation state of oxygen's -2. There are 4 oxygens, so that's going to be -8. The charge is -1. So what we've really now got is x minus 8 equals -1. Can you see that? Little bit, just sneaking in a tiny bit of algebra. X minus 8 equals -1. Therefore x is +7. Get it? Happy? Good. Okay. There are some elements that have got standard oxidation states that you're expected to remember. So, hydrogen is typically +1. Okay? Except when it's in H2, where it's 0, any element standard state 0. And I have seen this examined, when it's combined with a metal, okay? Then it becomes the hydride ion. It's not just sodium hydride, any metal. So label this up. When hydrogen is combined with a metal, okay, then its oxidation state is -1. Two other examples of that at A level, and they are NaBH4 and LiAlH4. Okay? Those are both contain hydride ion, which is H-. Okay, oxygen is always -2, apart from when it's an element, or when it's in a peroxide, such as H2O2, okay? Or when it's combined with fluorine. I said that earlier, didn't I? So when it's in a peroxide, it's -1, and when it's in a fluoride like that, or fluorate, then it's +2. Okay? It is exceptionally unlikely you will get examined on this, but should you, you need to know that. So, oxygen, -2, apart from in a peroxide or when combined with fluorine. Fluorine, -1, apart from when it's in a molecule with itself. Okay? Doesn't do any positive ones. Fluorine is Mr. electronegative, it's Mr. minus, therefore. So, let's just have a quick pause and you can all sit there and you can work those out. If we could pause camera, please. Okay. This one here, the +2.5, almost certain not to come up. The only... Can you just pause a second, please? So, you've got a quick bit of working out going on here. I don't think these are too hard, and you must be able to do them. Metals typically have positive values, but some of them have multiple different values. So manganese can be +2, +4, +6, or +7. Okay? Vanadium can be +2, +3, +4, +5. Non-metals are mostly negative, apart from when they're combined with oxygen. And that's where chlorine can be +1, +3, +5, or +7. Okay? Typically, it's about the number of you can think of it in terms of number of electrons you could possibly lose or possibly gain. So sodium is only going to lose 1. Its oxidation state, when combined with anything else, is always 1. This typically could be +1. This could be +5, up to +5 or -3, +2, +4, +6 or -2, +7, +6, okay, +1, -1, or +5, I think, +2, -2, +3, +5 or -3. Okay, if you think about it in terms of like nitrogen, it could lose 5 electrons or it could gain 3. Okay, and there are the answers to that. So here we have sort of standard bit of question. I mean, something like that, that's a 1 mark AS level question. You'd be expected to work it out in less than 30 seconds. Let's see if we can. Oxidation state of phosphorus there. Heard the right answer? 5. 4 times -2 is -8. Add 3 is -5, therefore phosphorus is supposed to be +5. And you are expected to be able to do it that quickly. Okay? Did I just lose a few people? No? We're okay? And so on. And there are the answers. Okay. There are therefore implications when it comes to naming it. There are 2 types of sulfuric acid. There's sulfuric acid 6 and sulfuric acid 4. Okay? Old name for sulfuric acid 4 is sulfurous acid. Okay? Here, sulfur 6 oxide means that it's the +6 oxidation state rather than the +4 oxidation state. SO2 and SO3 are both sulfur oxides. So SO2 is sulfur 4 oxide, SO3 is sulfur 6 oxide, and so on and so forth. So, lead 4 oxide, tin 2 chloride, antimony 3 chloride, titanium 4 chloride, bromine 5 fluoride. Okay. we started off by looking at definitions of oxidation and reduction. And I'm now going to give you a new one. Oxidation is the increase in oxidation state. So we now have 4 definitions for oxidation. They are addition of oxygen, removal of hydrogen, loss of electrons, and increase in oxidation state. Okay. So, what we now have to work out is whether something has been oxidized or reduced. If it goes from +2 to +3, it has been oxidized. If you go from there, oxidation state there, 0, oxidation there, oxidation state there. Therefore, this is reduction. Fluorine has been oxidized. We're going to have to work this one out. I think it's been oxidized, hasn't it? Carbon's been oxidized there. Okay, if we think about it, the oxidation state of carbon here, I think is it +3? Yeah? So it goes from +3 to +4. Okay, so it's been oxidized. That's a tricky one. Here, oxygen has been reduced. Okay, it's gone, no it hasn't, it's been oxidized. It's gone from -1 to 0, so it's been oxidized. Here, it's gone from -1 to -2, so it's been reduced. This one has been reduced. The chromium's gone from +6 to +3. This one here, nice little bit of Module 5 chemistry. Is this one here oxidation or reduction? Neither. Very good. +6, +6. Not redox. This one, did I hear what? This one here, +6, +4, it's therefore been reduced. Okay. If only reduction or oxidation occurs, so we can settle down please. If only reduction or oxidation has taken place, there must have been the addition or removal of electrons. For instance, go from Fe2 plus to Fe3 plus, go from a +2 to a +3 oxidation state. Oxidation is the loss of electrons, and to lose an electron there needs to be one change in oxidation state. So, in this case, Fe2 plus goes to Fe3 plus plus E minus. Happy with that? Okay. So, that is now a balanced equation, and this is called a half equation. Okay, a half equation, and the reason it's called a half equation is this can never happen on its own. If this is losing electrons, something else needs to be gaining electrons. So, here we have something going from +7 to +2. Still some muttering going on over there. From +7 to +2. How many electrons do you need to go from +7 to +2? 5. There they are. Okay? Is that even close to a balanced equation? No. Right. Rules for half equations. To balance a half equation, you can add H plus, water, and electrons. Okay? Probably worth writing that one down. For a half equation, you can add H plus, water, or electrons. Pause, please. If we go back and read the question again, it mentions acidic solution. Acidic solution means you've got H plus. If it said basic solution, you could have added OH minus instead. And what happens is the H plus reacts with the oxygen. And what's H plus and oxygen going to form together? Water. So, This is now a balanced equation. There are various ways of doing it, but I think that this is one of the very best bits of A-level chemistry, and I'll tell you why. There are two ways to do this problem. And I teach my pupils to do it one way and check it the other way. There's very little of the paper you can be absolutely rock solid certain you got right. But this is one of those bits that you can. What I tell my pupils to do is balance it using atoms, then oxidation states, and then check the charges. Okay? I.e., this is your starting point, MnO4 minus going to Mn2 plus. Okay? You balance it for atoms first. So you've got 4 oxygens on the left-hand side, which means you're going to need 4 waters on the right-hand side. If you create 4 waters, you're going to need 8 H plus to begin with. You stick them on the left-hand side. It's going from +7 to +2, which is reduction, which means you're going to need 5 electrons on the left-hand side. There they are. If this equation is now correct, the charges will balance. -1 minus 5 is -6, plus 8 is +2. Overall charge on the right-hand side is the right answer. Got it? Balance for atoms, then oxidation states. That should give you the correct answer, and then check the charges balance. If the charge is balanced, that's the right answer. Okay? So, there we have a particularly complicated half equation. There is some more here. Okay, so dichromate going down to chromium. This one's quite tricky because it involves 2 chromium atoms. But basically, you balance for atoms first. We've got 7 oxygens on the left, which means 7 waters on the right-hand side. 7 waters on the right-hand side means 14 hydrogens on the left-hand side. Don't be scared of the number. Okay? It's going from +6 to +3, which means I need 3 electrons on the left-hand side. Yes? No? +6 to +3, there are 2 of them. So I need 6 electrons on the left-hand side. Each one needs 3 electrons. Got it? And now my charges are balanced. -2 minus 6 is -8, plus 14 is... -8 plus 14 is +6. 2 times +3 is +6. My charge is balanced, that's the right answer. There are only really 2 that are properly hard. This one and this one. And they are worth learning by memory. Okay. Some work for you to do to just make sure that you're happy with that. I'm not going to go through those now. Here's the really hard bit. Balancing half equations. So, first thing that you do is you write out your 2 half equations. In this case, actually sorry, I just need to blow my nose. Can you pause for a second, please? Right. That beeped, yes, running? Yeah. Okay. An oxidation equation, half equation, is going to have to be combined with a reduction half equation. So here we have Fe2 plus going to Fe3 plus E minus. Happy with that? Here we have the manganate going down to Mn2 plus. Can we really stop whistling, please? These 2 can be added up. Okay? If you remember simultaneous equations from GCSE maths, we have now got an application of simultaneous equations. Just pause, please. Right. You know with with simultaneous equations, you have to make something equal on both sides so that when you add the 2 together, it gets cancelled out. Or you subtract one equation from the other and it gets cancelled out. You're doing exactly the same here because in an overall equation of reaction, there are no electrons. And what you need to make sure is the number of electrons on the right-hand side equals the number of electrons on the left-hand side. And to do that, you times this one through by 5. And now we have the same number of electrons on the left-hand side as we do on the right-hand side. Does that make sense? Add them up, cancel out the electrons, and there's the right answer. And what that shows you is one manganate ion reacts with 5 Fe2 plus ions. Okay? One of those reacts with 5 of those. Okay? Because this one's giving out 5 electrons, this one's taking in 5 electrons, this one's only giving out 1, so you need 5 of those to give out 1 electron each to fully reduce that. Does that make sense? And that is adding up half equations, and that is about as hard as this topic gets. Okay. Bit of work for you to do there. There are the answers, and that is the end of that session. If you can stop the tape, please.
Yeah.